Hello and welcome to CONF-APMM. This is our keynote speech on convolutional neural networks. I'm Marwan, Omar, Associate Professor of Cybersecurity and AI at Illinois Tech. Let's get started. So here we have some pictures that show you and some of the products that are actually based on convolutional neural networks or ConNets. So Google is using that. We have all these products. All of these are based on convolutional neural networks. You can also see here from this slide that CNNs are helping the blind, and this is the post here that we can look at. These are unrelated dog versus food. You can think of these as pictures here. And these are all also pictures of cats and dogs. So CNNs in 2012 supervision, also known as AlexNet. AlexNet won the ILS VR 2012 challenge. There was a major breakthrough with 15.3% top 5 error on ILS VRC 2012. Next best was 25.7%. This is an illustration of the architecture of our convolutional neural networks, or CNNs, explicitly showing the delineation of responsibilities between the two GPUs. One GPU, as we can see here, runs the layers part at the top of the figure here, while the other runs the layer parts at the bottom. The GPUs communicate only at certain layers. The network's input is 150,528 dimensional, and the number of neurons in the network's remaining layers is given by 250,440 to 186,624, and then 64,000, etc. Before deep learning, we had something like this, where we input pixels, we extract features from the face, and then we concatenate into a vector. So we vectorize these features, and we run them through a linear classifier such as SVM, support vector machine, to separate linearly, and then we get the answer. The last layer of most CNNs are linear classifiers. So this piece is just a linear classifier here. So we have the input text, we perform everything with a big neural network trained end-to-end, and we get the answer. So the key is to perform enough processing so that by the time you get to the end of the network, the classes are linearly separable. As you can see here, we have been able to separate the yellow from the blue, for example, 2 classes, or could be 3 classes. So you do enough processing so that by the time you get to the end of the network, you have linearly separable classes such as cats and dogs, or maybe 2 colors, blue and yellow, for example. ConVNets, they are just neural networks with 3D activations and weight sharing. So they share the weights, and they're based on 3D activations. Okay, so ConVNets, or convolutional networks, we can refer to them as ConVNets. They are just neural networks. They are a separate type or architecture of a neural network that is based on 3D activations and weight sharing. So what shape should the activations have? So we have X goes to a layer, then we have the height, and then layer H2, and then function. The input is an image here, which is 3D. We have the RGB channel, the height, and the width of the picture or image. We could flatten it to a one-dimensional vector, but then we lose the structure. What about keeping everything in 3D? So 3D activations before, we had the input layer, hidden layers, output layers. This is a one-dimensional vector before convolutional neural networks. Now we have 3D arrays. We have X H1, H2, etc. So this is a 3D activation with convolutional neural networks or conv-nets. As far as the 3D activations go, all neural net activations are arranged in 3 dimensions, as you can see here. All neural network activations are arranged in 3 dimensions. So we have the height, we have the width, and we have the depth, 3D dimensions rather than 1 dimension. For example, a CFAR or CIFAR 10 image, which is a dataset, very well-known dataset, is a 3 by 32 by 32 volume. So the depth is 3, the RGB channels, and then, so 3 RGB channels, and then we have the height is 32 and the width is 32 as well. 3D activations, again, we have the 3D activations here. But before then, as you mentioned, we had 1D activation, one-dimensional activation. So one-dimensional activation will be converted to 3D, 3-dimensional activations, 32 by 32 by 3, this is the RGB. A hidden neuron in next layer. So the input again is 3 by 32 by 32. The neuron this neuron depends on a 3 by 5 by 5 chunk of the input, part of the input. So this particular neuron will depend on a 3 by 5 by 5 chunk of the input. The neuron also has a 3 by 5 by 5 set of weights and a bias or scalar. An example, consider the region of the input XR, right here, XR, with output neuron H hyphen, H here, that's the output. Then the output is HR equals the sum of HR plus the bias term. Then the output is HR as we mentioned, so we will take the same, the sum over 3 axes. Okay, as we've mentioned, a hidden neuron in the next layer here. So we have H1, H2 with the 2 output neurons. If we have 2 output neurons, you will have H1 and H2. HR1 equals L. That's the mathematical equation. B1 is the first bias term. B2 is bias term 2. Then we take the sum of all the weighted average. And this is the depth of dimension here. So we can keep adding more outputs. Rather than 1 output neuron, we could have 2, 3, 4, 5. These form a column in the output value, the depth times 1 times 1. Each neuron has its own 3D filter here and own scalar bias. So each one of these neurons will have its own filter, 3D filter, and its own bias term or scalar. So now we can repeat this across the input. D is sets of weights, also called filters. So we have a set of weights or filters. Weight sharing, this is one of the characteristics of convolutional neural networks or CNNs. Each filter shares the same weights, but each depth index has its own set of weights. Each depth index has its own set of weights. As you mentioned, each filter will share the same set of weights. So these sets of weights, also called filters, with weight sharing, this is called convolution, right? Weight sharing, we call it convolution. Without weight sharing, this is called a locally connected layer. If we don't share the weights, it will be considered a locally connected layer. So one set of weights gives one slice in the output here. So we have output of one filter To get a 3D output of depth 0, use 0 different filters. In practice, ConvNets use many filters, 64 to 1024, more than one filter. So this is the input depth, this is the output depth, more than one filter. In practice, as you mentioned, these ConvNets will use more than one filter, many filters, anywhere from 64 to 1024 filters. Altogether, weights are four-dimensional. We have the output weight width, the input width, the kernel height, and the kernel width. So these weights will have four dimensions. We can unravel the 3D cube and show each layer separately here. So these are the different layers. One filter is equal to one depth slide. One filter equals one depth slice or activation map. So we've got 32 filters. Each is of size 3 times 5 times 5. We got 32 filters. 1, 2, 3, 4, 5, 6, 7. So we've got 4 times 7, that's 28, 29, 30, 31, 32. So we've got 32 filters. Each one of them is of size 3 times 5 times 5, which is just a slice of the input. So these are the activations. Again, they will go through these filters. So this is the last one here, 3 by 5 by 5. This is the last filter here. So as a recap, a ConvNet is a sequence of convolutional layers, right? Interspersed with activation functions and possibly other layer types. So we've got 32 by 3 times 32 times 32, convolutional or ReLo example 6 would be 5 times 5 times 3, as you mentioned, filters, another convolutional layer here, and then, so this one would be 10 times 24 times 24, and so on and so forth. This is the height, 32, the width is 32, and the depth is 3, as you mentioned. This is one of the filters, right? Each filter is size of 5 times 5 times 3, which is just a chunk of that input. So convolve the filter with the image, slide over the image spatially, computing dot products. So here we have filters always extend the full depth of the input value. The filter with the image, again, slide over the image spatially and compute the dot products. The result of taking one or a dot product between the filter and a small 5 times 3 chunk of the image, also known as 5 times 5 times 3 equals 75-dimensional dot product plus the bias term. Always add the bias term. So this is the activation map here. So we've got a green filter here. And we have got the activation maps here. Again, the images of size 32 times 32 times 3. 3 is the depth. So if we had a 6 by 5 and 5 filters, we will get 6 separate activation maps, as you can see here. All of these are activation maps. 1, 2, 3, 4, 5, 6. We've got a convolutional layer here. So we stack these up to get a new image of size 28 by 28 by 6. All of these are activation maps. There are some demos here that we can look at from Stanford University. So during the convolution, the weights or slide along the input to generate each output. So this is the input and this is the output. So these are the weights. So each position, as you mentioned, we are doing a 3D sum. So HR equals the sum of all of these. Channel, row, column, plus a bias term, as we have mentioned. But you can also convolve with a stride. The example stride equals 2 here. Notice that with certain strides, we may not be able to cover all of the input. The output is also half the size of the input here. As you can see here, the output is half the size of the input here. We can also pad the input with zeros. So pad 1 and stride is 2. So pooling, for most nets, convolution is often followed by pooling, which creates a smaller representation while retaining the most important information. The max operation is the most common, max pooling. Why might AVG be a poor choice? So here we have a 32 by 32, we downsample to 16 by 16. As you mentioned, we have the max pooling. So it makes the representations smaller and more manageable with pooling. We make the representations smaller and more manageable. It operates over each activation map independently. So we downsize or downsample from 224 by 224 to L 112 by 112. We have the single depth slice with max pooling with 2 by 2 filters and stride 2. What's the back propagation rule for max pooling? In the forward pass, store the index that took the max. The back prop gradient is the input gradient at the index. So we have an example convnet here. We have the convolution here, the reload, convolution, reload, and max pooling here. This is a truck or a car, airplane, ship, or course. It will be most likely a truck, as you can see. So we repeat this until we get to the output, fully connected ladder, FC, fully connected. So 10 by 3 by 3 count filters, stride 1 and pad 1. We have 2 by 2 pool filters and stride 2. So this is an example from AlexNet from 2012. So we have one sample, 227 by 227 times 3. So it will go to 96, 55 by 55 down sample, and then 27 by 27, 13 by 13, 13 by 13, and until you get to a fully connected layer, and the class will score 1,000. So extract high-level features here, and we classify each sample. Max, again, max pooling norm, local response normalization. 4 means fully connected. This is just another diagram showing here how to train convolutional neural networks. How do you actually train these things or these networks? Roughly speaking, you gather labeled data, you find a CONF-net architecture, and we try to minimize the loss. So we split and pre-process the data. We choose the network architecture, as you mentioned. We initialize the weights, find the learning rate and regularization strength. We minimize the loss and monitor the progress. We fiddle with the knobs. Mini batch gradient descent, sample a batch of training data, about 100 images, do a forward pass, compute the loss average over batch, backwards pass, compute the gradient. So we have the forward pass to compute the loss, and then you do backward pass to compute the gradient, update all parameters. Note that usually called stochastic gradient descent, even though SGD has a batch size of 1. Gradient of stochastic gradient descent, or SGD for short. So regularization will reduce overfitting. This is a very important feature. So we can visit this website for more information on understanding regularization. So this is just an example that shows you how to train deep connects in your browser, as you can see here. You can train an MNIST digits autoencoder. You can do reinforcement learning with deep Q learning. You can do interactive regressive toy with one-dimensional. You can do comparing stochastic gradient descent with ADA grad, with ADA delta. You can do neural network paints as an image. So you can do all kinds of things here. You can click here on getting started, documentation, intro. So if we click on interactively regress toy one-dimensional data, for example, and you can click here, fully connected layer, ReLaw, fully connected sigmoid function. You can click on also draw outputs of a layer. As you can see here, FC changes, fully connected layer, ReLaw, FC sigmoid function. And you can regenerate data here. You can type 100 here. More data points here. You can change the network. Here. And you can go back here. You can click on this image, for example, ConNet. So you have your learning rate you can change. You have the momentum, the batch size, the weight decay. You can see here. You can load a pre-trained network, which achieves 80% accuracy. Instantiate a network and trainer. These are different layers. The stride, pad equals to activation equals ReLaw. And you can click on change network here. So these are the activations, max activation. These are the activation gradients, the max gradient, the parameters, the filter size, pooling. So we have the test accuracy based on the last 200 test images. These are example predictions on test data, and this changes because it keeps working here. The numbers are working here. And you can pause it, of course. As you can see here, the loss is going down, then it's going up a little bit. You can save the network, you can initiate network here. You can change some of these. You can click on pause. So this is a very interactive web-based tool. Overfitting, modeling noise in the training set instead of the true underlying relationship. So insufficiently modeling the relationship in the training set. General rule is that models that are bigger or have more capacity are more likely to overfit. So you split the data set into train, validation, and test, gradient descent, and fine-tuning of parameters. So you train your network with the gradient descent and you fine-tune it. Also, you validate, you determine the hyperparameters like the learning rate, regularization strength, etc., and pick an architecture. For the test, you estimate the real-world performance example would be accuracy, which is the fraction of correctly classified samples. We have to be careful with false discovery. To avoid false discovery, once we have used a test set once, we should not use it again, but nobody follows this rule since it's expensive to collect data sets. Instead, try and avoid looking at the test score until the end. And this brings us to the end of this speech. Thank you so much for your time and attention.